So, tell me the difference. L1, L2, L3 cache.
Is the fastest.
L1 fastest. Okay? Why is fast memory good?
Because it's just good.
Faster the better, right? We can do really, really, really quick operations. What about L2 cache?
Still fast.
Still fast, but a little
A
slower.
little slower than L1.
Okay, what about L3 cache?
Slower still.
Okay, is that it for L3? What about capacity? How big is
It's
L3
bigger.
cache compared to
Bigger.
L2 and L1?
Yeah, it's bigger. Much bigger.
So typically L1 cache is the smallest. L2 cache is a little bit bigger. How big is L3 cache? It's typically at least the size of L1 plus L2 cache. In fact, usually it's actually a multiple of L1 plus L2 cache. Why is it? What do we actually use L3 cache for? Yes, it's slower than L1 and L2, but it's still fast. But what's its purpose? When was L3 cache introduced? What was the advent of the necessity for L3 cache? Multiple cores. So how is L3 cache used?
Isn't it shared between all the cores rather than L1 and L2, which are core specific?
L1, L2 are caches that are core specific. L3 cache is a larger pool of memory that's still very fast that's shared among the multiple cores on a processor. So that potentially two cores can be working on the same task and sharing data between the two of them using L3 cache. That makes sense? So L3 cache is fast memory for multiple processors. Okay? So that's kind of the big difference there. All right. How a modern computer works. Thread of execution. Add a slide here. Just a good one. What's a thread? We've probably all heard of threads before, right? It's one of those buzzwords. How many of you have never heard the term thread as it relates to computing? Not thread for sewing, but never heard it? Okay. You have heard of it? Okay. But the question was, how many of you have never heard of it? Why'd you raise your hand? All right, so what is a thread then? You can answer the question you rose your hand for now. What is a thread? I heard it's a process or it's a touch. That was the entirety of the answer. I'll accept it. I remember that in high school. We were taking our driver's ed, like the written test. And, it was one of these things where, like, we switched papers to grade each other's paper. And this one guy was in the class. I don't remember his name, but I guess he had just terrible handwriting. And some other person in class came up to the teacher and was like, I can't read this. And the teacher's like looking at it and says, okay, it says bus, then looks like cheese. I'll accept it. Hands it back. All right, anybody else? What's a thread? Go ahead.
It kind of fakes having an extra core, multiple cores, by giving a certain amount of time to each process that needs to be processed.
Okay, I don't think that's wrong. It's kind of a roundabout. Okay, so a thread is a bucket of execution where anything within the bucket executes when this thread has CPU time. So, punchline being, it's kind of the mechanism. I'm not sure faking out is the right term, but it's the mechanism by which more than one thing can happen at one time. Okay? So, that's a thread. Now, sometimes, and this is maybe where the fake out thing comes into play, some threads literally execute at the same time as another. Some threads literally execute at the same time as another thread. But potentially, you can have more than one thread seemingly executing at the same time, where as programmers, we can create threads of execution and have more than one thing happening at the same time. But in actuality, the CPU is just cycling through all of our different threads, giving it so much time, which I think is what you were saying. Okay, so
It makes the multitasking thing.
threads themselves don't fake the multitasking. Threads themselves are containers of execution. It's the CPU scheduler that actually fakes the multitasking. If you had a single core and you had 5 things trying to run at once, each one running in its own thread of execution, its own bucket, the CPU would give each of those threads a little bit of time and cycle through them really, really quickly so that the people, the end user who was experiencing the operating system would be fooled into thinking all these things are happening at the same time. That's a feature of the CPU scheduler, not a feature of the thread. The thread is more of a means to an end. Okay, there's nothing special about threads other than that they're containers to hold some execution. That makes sense? And kind of show a quick example of this. Let me, do I already have a thing in here for this class? I don't. Oh, why am I selecting a wizard? I selected Java project. Oh, I tried to select Java project, but my shakes kicked me down. I promise I tried to click Java project. Okay, so we'll create a, what's it complaining about there? What? Here's a situation where I think indeed Eclipse is broken. Hold on. Let's give the old girl another chance. Let's try to run this real quick. Okay, so that works. This is very strange. That's an excellent question. Let's try just making this again real quick. I have a feeling that something didn't, something was skipped. Okay, were we using the right, is that it? All right, so we're good now.
That's exactly the same thing that you were typing earlier.
Yeah, I think it was because I had the wrong Java runtime environment selected. I must at some point gotten the shakes and clicked the wrong thing, and everything was broken from that point forward. So in any case, I'm going to go ahead and I'm going to create a second class here. And we're going to call this guy a WorkerBee. And WorkerBees are going to have a name. Okay, and then we're going to have a and here I'm actually going to give a second variable called count. And for every worker bee, we'll have count be 0. We'll start it off. Okay, so by default, we're going to create this worker bee. Now I've created this intentionally incorrectly right now so we can see how not having threads hurts us. So we have a class called WorkerBee. This guy keeps track of 2 variables, a name and a count. When we create a WorkerBee, we're going to pass in its name. So maybe it's WorkerBee1, WorkerBee2, WorkerBee3, so on and so forth. Each WorkerBee will have its count variable, which starts off at 0. And then we're going to tell a WorkerBee to run. And what does the run method do? It creates an infinite loop that prints out who's counting and what the current count is, that increments count. Make sense? So that's all our little WorkerBee does right now. So I'm going to go into driver. We're going to go ahead and create one WorkerBee. WB1 is equal to a new WorkerBee number 1. And then we'll say WB1.run. And it's going to start, so it'll say WorkerBee1, 0, WorkerBee1, 1, WorkerBee1, 2. Make sense? Okay. So we're going to go ahead and create a second WorkerBee now. And this is going to be WorkerBee number 2. We'll call this guy WB2. And we'll have WB2.run. What's the output of this program going to be? Okay, well, what about WorkerBee2? We're not going to get to that guy. Anybody not agree with him? Okay, we'll run it. He's right. Always WorkerBee1. But I really want to have 2 separate WorkerBees. I want both of these guys to be doing their job at the same time. This is an example of how early operating systems worked. When you had single programmed operating systems, or single program operating systems, as opposed to multi-programming operating systems. So if you launched Microsoft Word, you couldn't launch another program because only one program can run at once. So in this case, I have 2 programs, 2 WorkerBees, and I've told each of those guys to run, but only one guy does any work because the second guy can't do any work until the first guy ends. But the problem is that the first guy is in an infinite loop. He'll never actually end. Now, for a long time, this was normal in computing. That make sense? How would I work around this? Let's say that I wanted to create a situation where both worker bees did their counting.
Are we allowed to use the built-in threads in Java?
Without threads. I'm going to show you threads here in a few minutes. So without threads. So we're going back in the early days of computing, trying to find a workaround without having the thread. So we want to have a situation where both worker B1 and worker B2 are both counting. How would we fake this? Well, in real life, we'd create a manager, right? So a manager would manage 5 worker bees, and he would say, okay, you work, now 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 you over and over and over again, right? So we'd have a manager worker bee who then created 5 normal worker bees and told each worker bee to do their work. But still only one worker bee can happen and can work at an individual piece of time.
Wouldn't it be more efficient just to use recursion so that 1 goes to 2 and 2 goes to 1? Or 1 goes to 2 and 2 goes to 3, 3 goes to 4, and 4 goes to 1?
Okay, why do you think that'd be more efficient?
Just because you're going to eliminate the fact of someone just telling everybody what everyone's going to do. Because you're immediately going to that next step, you're not exiting out of and then going back.
So take the manager out of the equation, have each worker responsible for the next worker.
Yeah.
Okay, that would be okay, but you wouldn't want to do it recursively. You'd run out of memory real quickly. But yeah, instead of having a one manager telling each worker, you'd have each worker telling the next worker that I finished my job, now it's your turn. Okay, what's the downside with that though? Each worker only accomplishes exactly one thing. Right? So if each worker is going to print out their name followed by the current count, then increment count. That's their job. And worker 1 is going to do that. They're going to say worker 1, 0. Now my 0 became a 1. Then I tell worker 2, go. Worker 2 says worker 2, 0. Then his count is now what? Worker 2 tells worker 3, go. Worker 3, 0. His count becomes 1. Worker 3 then tells worker 1, I'm done. Worker 1 says, worker 1, 1. Count becomes 2. He tells worker 2, so on and so forth. So now we're doing little bits of work each time. Now our program's going to run relatively quickly, so it might seem like they're both happening at the same time, right? But you will see very specific. I mean, you'll see worker B1, worker B2, worker B3, worker B1, worker B2, worker B3, worker B1, worker B2, worker B3, each doing their one little task. You're going to be spending time them whispering to the next guy to go and work. Okay? So in that particular case, it's very clear that only one dude's working at once. The job of our operating system, the job of the CPU is to run really, really, really quickly to fake us out such that more than one thing is happening at once. So at least we think more than one thing is happening at once. Okay, and that's where threads come into play. Threads have the built-in magic. So our modern operating systems have a thread subsystem. And the thread subsystem knows how to have one program that is the manager. So if we think about our CPU, the CPU has a bunch of, our computer has a bunch of programs running. So let's say we have 5 programs running on our computer. The CPU manager, the piece of software that manages the CPU, which we'll talk about how that actually works, that guy is going to be in charge of managing those 5 programs. The thread subsystem is something that lives within each program. So each program then is responsible for managing its own set of threads. So let's just, as a simple example, say each program is getting 5 seconds on the CPU. Something like that. Okay, so Microsoft Word gets 5 seconds of CPU time. And let's say that Microsoft Word happens to have 5 threads of execution running. And for a simple example, and in an act of fairness, it's going to give each of those threads 1 second of its 5 seconds. So one of the threads is going to run for a second, another thread's going to run for a second, so on and so forth. So Word is actually responsible for managing its threads within it. The CPU manager is responsible for managing Word and how long it gets CPU time. That make sense? Okay. So if we're going to write this as a thread model, when we create a WorkerBee, we're going to say that this guy extends thread. There already exists in Java a thread class that has the appropriate magic within it for running threads. Okay? And I actually don't have to change anything in here because I happen to create the method with the correct name. Okay, so you must have a method called public void run. And to show you this real quick, if I go to the Java documentation, and it lives inside of java.lang, so you don't have to import anything special. We'll go down to thread. And threads, they implement a interface called runnable. And the runnable interface dictates that you have a single method called run. Now inside thread by default defines its own run method because it implements runnable, so it has to have its own run method. And this run method does nothing. So if this thread was constructing using a separate runnable object, then that runnable object's run method is called. Otherwise, this method does nothing and returns. So the default run method for a thread doesn't do anything. It's there to be overridden. Okay? The method we're going to use for threads, though, is the start method. This causes the thread to begin execution. The Java virtual machine calls the run method of this thread. So this is the magic method that does whatever needs to be done to actually spawn off a thread and have the current Java program, the main thread of execution, now manage this particular subthread of execution. All right? So inside my run method, for each of my worker bees, I now have my infinite loop that just keeps printing out their name and the current count. All right? So all I've done here is put extends thread. So now this guy is a thread instead of just being a normal object. So when I go back to driver now, instead of calling the run method directly, I'm going to call the start method, which is the magical thread method that knows how to start a thread in the correct way. Before, this line blocked this line. We did not get to the second wb2.run line because this one never ended. So it was a blocking line. Now, because it's threads, this line no longer blocks. So we're going to see when we run this now that we'll have both threads interchangeably working. And you might see 4 or 5 thread 1s, you might see then 4 or 5 thread 2s, you might see them mixed together, but you can kind of see how both of them are seemingly working simultaneously. See it flipping back and forth there? Okay, so we have 2 threads of execution, 2 separate things happening at potentially the same time. Now, realistically speaking, do you think those 2 things were actually happening at the same time, or just faking us out that they're happening at the same time, and why? There's an underlying explanation either way. So either of those answers is an acceptable answer, but explain why it might work that way. So why might we be able to say that both of those threads are actually happening simultaneously? What's an argument for that? Go ahead.
Threads could be on the different cores.
Okay. Each thread could be on a different core. You know, that's making the assumption that the thread manager, that is this program, has access to those cores, but, you know, potentially each thread is on a separate core of the separate physical CPU resource. And therefore, it would actually have its own execution time. Now, the alternative argument is if both threads are running on the same core, only one thing can possibly happen at once. So that core is just doing its work really, really quickly, and we think that that thread is happening at the same time. Right? Can we tell which it is by looking at this? If I start this running again. Because there's a third thing to take into consideration here that we've learned about in here. So we certainly see it flipping back and forth, right? Does that tell us whether or not they're happening simultaneously or not? Is that enough information? Does anybody want to actually say no? Then I'm going to ask you why. So you're committing to the follow-up question. We've had very, very poor voter turnout recently. Why is that not enough information to tell us whether or not those things are running at the same time? I mean, clearly, as we watched it, it was flipping back and forth, and not necessarily just, 1, 2, 1, 2, 1, 2, 1, 2. We kind of see it going in streaks, right?
Can something print two things it's not possible to print two things at the exact same, at least as far as from us seeing it.
Tell me about that. How does printing work? Printing is an I/O function, right?
Yeah.
What have we learned about I/O functions in here? Well, they are expensive, that's true. We talked about interrupts. CPU is not going to waste time on an I/O function because they're expensive. So a CPU is going to interrupt itself or get interrupted whenever there's an I/O operation like print something to the screen. And that's going to go to the subsystem for working with the graphics card and displaying something to the screen. So could two things be working on separate processors and still only one thing and still have them flip back and forth like this? Is that possible? As opposed to having two things working on the same processor and having them flip back and forth like we're seeing? When we look at it like this and we see them flipping back and forth, does this really give us any valuable information as to whether or not these guys are running on a single core or multiple cores? Because only one thing can print to the screen at a time. And who gets to print? These two guys are fighting over a single resource. They're fighting over the resource that displays crap to the screen. And who gets to use the resource? Whoever got there first, right? So if one guy happens to get there first, even if they're running on separate cores, the other guy's going to have to wait in line for that resource. Somebody's currently using the ATM. Okay, you cannot use it at the same time. So this is a shared resource. So the first guy's going to get to print, and only when he's done, and he goes and gets back in the line for the CPU to increment count, to make count go up by 1, will the other guy get to do his time on the CPU. Now, given that, can we make a guess about whether or not this is running on one CPU or two? I guess we could say or more. This has 4 CPUs, but I'm going to say this is likely running on one processor. And we likely have enough information here to make that an educated guess. Why is that? Given what I just said, that these two threads are competing for one resource, whether they're running on one processor or two processors, these two threads are competing for a single resource. What are we seeing in our pattern here? Are we seeing 1, 2, 1, 2, 1, 2, 1, 2, 1, 2? Or are we seeing a bunch of 1s followed by a bunch of 2s followed by a bunch of 1s followed by a bunch of 2s? Second one. Now, we're not guaranteed to go 1, 2, 1, 2, 1, 2 if they're both running on separate processors. Even though they're competing for the one resource, they're also competing for that one processor, or for their individual processors with the other programs that are running on those processors. So we wouldn't necessarily think that we'd see exactly 1, 2, 1, 2, 1, 2, 1, 2. We might see some streaks, but we should see a relative when they're both running on their individual CPUs at the same time, and they're both competing for the single print resource, the single I/O resource at the same time, we would expect to see them, struggling for that resource, kind of bouncing back and forth. Where when we look at this, we clearly see runs of 1s and then runs of 2s. So that likely indicates, unless we just have really bad luck, that this guy's running on a single CPU. And each of those, our Java program, actually really the Java virtual machine is running on the CPU, and the Java virtual machine is getting X amount of CPU time that it's sharing among this particular program. This particular program is then going to take its, let's just use as an example, 5 seconds of CPU time. It's likely much less than that, but let's just use 5 seconds as our example. And he happens to have 2 threads that he's responsible for. So what's he going to do? He's going to say, oh, I have 2 threads. I'm going to give you 2.5 seconds. I'm going to give you 2.5 seconds. So the first thread's going to have his 2.5 seconds, and he's going to go and print, do work. Or he's going to run on the CPU, say, I need to pause, go and do his I/O, then come back to the CPU. Now, when that guy's off the CPU, what's happening? When that thread is doing its I/O, the other guy might get to use the CPU, right? Does that seem like it's what's happening here? Since this program as a whole is interrupted because of an I/O request, the entire program has to go back into the waiting queue and wait for the CPU again while this guy does his I/O. And then he gets the CPU again. So that's why we're seeing streaks. We have thread number 1 getting some time, and then thread number 2 getting some time, then thread number 1 getting some time, then thread number 2 getting some time. That's all interwoven into the top level thread, that is the thread associated with our program driver, getting its CPU time from the Java virtual machine, which is getting its CPU time from the CPU manager. Does that make sense? So we can make a fairly educated guess that since we see this being streaky, this is probably all running on one CPU, and because I/O is expensive, we're actually visually able to see CPU scheduling. See it give a little time to one process, a little time to another process, a little time to another process, so on and so forth. But since I/O is so expensive, which I've shown before, just to give you a quick, I just won't start these 2 guys, so we won't have those. If I have an int count is equal to 0, and I say for int I is equal to 0, actually we don't need a count, we'll just do it with I. Actually I do need the count for my entire example. I is less than 10 million, I plus plus, and we'll say system.out.println count, then we'll say count plus plus, and then we'll throw a final system.out.count after the loop. All right, so all this guy does is it prints out all the numbers between 0 and 10 million. That's what this current program does. And we run this, and it's going to take some time to run. Okay? As opposed to me not printing in the middle, but just doing counting. Did we just experience the speed difference that I/O plays in there? When you print something, it's expensive. So when I'm printing something, every single time I count, I'm interrupting the processor and saying, whoa, I need to go print something. Be back in a second. 10 million times. That make sense? Okay, so I/O is very expensive. So because of this, we were able to sort of see CPU scheduling, experience it in slow motion, if you will, because we are printing across 2 threads. And each of those threads was competing for CPU time, we can say. All right, questions about that? So before we had threads, we couldn't have more than one program running at once. That's actually a half lie. Before we had threads, we had a different type of way of doing this. And it was called, and make sure you listen very carefully to how I enunciate it. It was called forking. Okay. We had a keyword called fork. And the fork keyword you would have one program, and when it forked, it would split into 2 copies of itself. Where are your people's heads? Just in the gutter. Okay? So you'd have a single program, and that program would make a copy of itself using the fork command. And after that, the fork command returned an integer. And after the fork command, you'd have 2 copies of that program. And the program wouldn't know whether it was the original or the clone. So the value that was returned by the fork command was a process ID. And the original would have a process ID of 0. The child, the new one, the clone, would have a process ID of something not 0. Okay? So the parent could decide, okay, I'm going to keep doing this. This is my job. And the child could decide, oh, I'm the clone. I'm supposed to do this crap. So it would be like an if-else statement. All right? So that was the way we did it before threads. We might call threads lightweight processes. We're going to talk about processes in more detail when we get to CPU scheduling. Right now we're looking at an overview of the whole operating system. But when you use the fork command, you would literally get 2 separate processors, 2 separate programs, full-fledged programs running on the CPU. Each of those programs getting its own CPU time. So you didn't have this model of one program having to manage a bunch of threads. You had, if you created 30 programs, now your CPU, the CPU manager is having to run 30, having to facilitate 30 different programs. And you can do this in a language like C. And it's actually a very quick way to crash a computer. So what if you had a whole bunch of programs that just did infinite loops? And each one of those maybe printed stuff out to the screen. That way you really monopolize all the resources you possibly can. You're monopolizing the CPU, you're monopolizing the I/O as well. And all the parent process did is it kept creating clones. You guys really wanted me to say it kept forking clones, didn't you? The dean gets a hold of this. All right, so it just keeps creating clone after clone after clone after clone, and each one of those clones just keeps printing crap to the screen and adding one. So now, before you know it, you have millions of processes all competing for the single CPU. And each one of those processes is getting its own CPU time. And each one of those processes is completely trying to monopolize the I/O substructure. Now, all your other programs that you really want to be responsive now are not responsive. It's not because their computer is bad. The CPU's job is to fake us out, to trick us, to make us feel like all the programs are running simultaneously because it's so fast. But now you're going to have 10 million programs open at the same time. That's more clicks than we could really accomplish in a day, right? Or in a month. So you're going to have 10 million programs open at the exact same time. And the CPU is going to try to be fair to every one of those 10 million programs. I'm going to give you a little CPU time, and you a little CPU time, you a little CPU time. Over here, Microsoft Word is waiting in line. He's number, 9,462,321 in line before he gets CPU time. It's going to become unusable. And the computer's gonna, and the computer's gonna end up into deadlock, where it becomes unusable. It hasn't actually crashed, but you're gonna have to reboot it to get that running program that keeps making clones out of memory, so it's not running anymore. That makes sense? So, I mean, these were realities years and years and years ago when, you had computer hackers, virus writers who had direct access to a computer. If I was, when I was an undergrad, I had a shell account with a Unix server called UXB. Nothing would have kept me from telnetting into UXB, writing a 5 or 6 line long C program that would have brought the entire server down in almost no time. Now, the virus writers have it more they have it harder. Because now they have to figure out how to get you to double click on something or something to get their program launched. Now, would it have been very smart for me to log into my own personal account on this shell thing and run this virus program that brings down the server? They would have certainly gone in and looked at the last process that we're running before the death of the server and seen that, oh, Mike Littman wrote this program and it got out of control. And then it would have come back on me and I would just play dumb. Like, oh, I'm a beginning programmer. I don't know what I'm doing.
Is this the true story?
No. I was never a bad programmer. Right out of the womb.
Did you ever claim to be a bad programmer?
No.
He was the only one who had a legitimate purpose for creating a Hello World program.
Yeah, my first word was the Hello World program. All on one line. As a word.
When you dropped your, not dropped, went into the water with your...
My phone?
Yeah, when you went to the store, we were like, oh, yeah, I don't know, it stopped working.
Oh yeah, I definitely played dumb there. Like, look, I don't even know. It's almost like the thing went swimming in a pool. But I gave up that real quick as soon as the first thing they did is they took out the micro SD card on the side, or the SIM card rather. They have the Apple devices have like a moisture detector thing, and water poured out. Like a little pool of water poured out of the phone. And yeah, it's like, well, I guess I dropped it in a puddle or something at some point. They didn't even have to check the little moisture detecting dot when they saw water pour out onto the table. I'm pretty sure this is not under warranty. Yeah, very entertaining. Okay, so we get the purpose of threads as opposed to forking. So I'm just going to add to this real quick. We can say a thread is a lightweight process, where a process is a full running program on the CPU which gets its own CPU time. Good enough explanation for now until we actually get into CPU scheduling. Make sense? All right, so next time we're going to quickly gloss over the symmetric multiprocessing stuff, since we already talked about some multiprocessor things, but we'll just kind of talk about how the caches work with, right in here we'd probably insert L3 cache before memory. So memory is kind of a catch-all there. And we're going to try to get to the end of this slide set so we can start getting into the actual individual working components of the CPU. We're talking about everything at a high level right now. And then we're going to talk about at the individual level how memory management works, how CPU management works, how file system management works. All right? Questions, comments, concerns, bribes? I will see everybody on Friday.